Physics Bites,
a science podcast in English
by the students of Notre-Dame d'Ascension.
Hello and welcome to a new episode of Physics Bites, our English language physics podcast from the students of Notre-Dame d'Ascension here in Paris. We're here with two new students in our senior class who are going to be talking to us about dark matter and dark energy. I also have a new co-host who we'll get to her next. Do you guys want to introduce yourselves?
Yes, hi, I'm Domitille. I'm an astrophysicist at the University of La Sorbonne.
Recently appointed, right?
Yes. And I'm Jeanne. I'm also an astrophysicist, but I work for the European Space Agency.
Right, also newly appointed. No, you actually worked with them last year, a couple of years ago. And my co-host?
Hello, my name is Maud, and I am the co-host for today.
And you have no university appointments yet in astrophysics? Soon.
Come soon.
Yes, soon enough. All right. Well, we have such experts with us today, so why not get straight to it? Do you guys want to talk to us about dark matter first, maybe? So we put the two together because they're kind of similar, but at the same time they're very different. And you guys did a really good presentation, going back and forth between the two of them, giving us a lot of information about where the theory comes from, and then experimental tests for it. So let's get into the details. Jeanne, do you want to start?
Yes, of course. Well, about dark matter, we discussed about the history of the discovery of dark matter. We realized that the idea of dark matter was first thought like a couple of years ago. It was in 1884, and it was
a couple of hundred years ago.
Yeah, a couple of
years ago is when you got appointed to the ESA.
Yeah, exactly. In 1884 with Lord Kelvin, and then.
So, what motivated Lord Kelvin to come up with this idea? Like, what was the instigating event?
Well, he wanted to discuss the potential number of stars around the sun. And he realized that many of the supposed 1,000 million stars were dark bodies, but he doesn't really explain why he thought that.
Okay.
Well,
so it's not really dark matter in the modern sense of the word, but the idea of matter that we can't observe is the first, right?
Exactly.
Okay.
And the first evidence of the existence of dark matter, if we really can call it evidence, is with Fritz Zwicky.
Right.
In 1933. He applied the virial theorem to the comet cluster, which is a cluster of galaxies which is like 351 million light years away. Okay.
Do you want to just give us a very brief, simplified idea of what he observed that made him think about there must be something there that we can't see?
Well, he observed that the speed of the orbits around the comet cluster was not okay compared to the mass of the comet cluster. He realized that they were spinning much too fast, and there had to be some other mass that we couldn't see.
So the idea being that from like classical mechanics, the speed has to change the further it goes away, unless there's like some extra force or something else present. And so what you're saying is that what he observed was that at the distance that they were doing their revolutions around the center, these stars, or this galaxy, I guess, in a way, was not doing what it should.
Yeah, exactly.
And it could only be explained if there was some extra mass that we couldn't observe.
Yeah, and he realized that the missing mass was hidden from the view, and he estimated that the cluster had about 400 times more mass than it was visually observable.
So in order for the speed of rotation to work with classical mechanics, the mass would be much, much higher than just the mass of the stars that we can see.
Yeah.
Okay.
And that's...
So this was in 1933.
Yeah, 1933, and that's when the first researches about this topic started. And as we are looking for a lot of mass but that we can't see, we know that we are looking for particles that are very heavy but that interact very weakly with other particles.
What do you mean by interact weakly with other particles? What is a way of visualizing what these interactions would be?
Like with light and with electrical fields and magnetic fields, they interact weakly with
Right.
Like,
And the weaker the interaction, the more difficult for us to observe
Yes.
any consequences of that interaction,
Yes.
right? So it makes it more difficult to indirectly prove their existence or at least make measurements about their properties. Okay. So we'll come back to maybe dark matter later. Dark energy. So it has dark in there, so it must be related, but not really.
Well, yes.
Domitille.
So we talked about dark energy when we had to explain some phenomena in the universe that were like contradictory to the laws that we have in
Right.
physics today.
So in a way, it's similar in that you're saying that we observed things that did not correspond to what the laws of physics at the time would have us
Yes,
accept.
because we thought for thousands of years that like the universe was static and eternal, which means that it was finite in
Finite, yeah.
finite in space and in time.
Mhm.
But some discoveries
And not changing.
and not changing. But some discoveries in the 1920s were made that proved that the universe was expanding.
So who's at the origin of these observations? Who's most well known because of this work?
Edwin Hubble
Right. The
with
famous,
the Doppler effect.
right. Not the Hubble effect, you mean, not the Doppler effect.
Yes, but he explained
used-
the Doppler effect to create his Hubble effect.
Okay.
And we found out later that its expansion of the universe was accelerating. And that was kind of weird because we know that the gravitation is a force that pulls objects together.
Right.
So we had to explain why the universe was expanding when the gravitation was pulling things together. And so we came up with the idea that there was a force out there that was making the universe expand, and we
Right.
called
So,
dark energy.
so if we go by the laws of physics, when there's gravity, it should be slowing down the expansion of the universe.
Yes.
So not only do we not see that it's slowing down, we see that it's getting faster and faster. Do you have any way of telling us how this observation was made? How do we find out that it's getting faster, the expansion?
So a group of scientists decided to measure like the speed of the expansion in the past, and they used a type of supernova, which is like a massive group of stars, and they used it as a simple standard candle, so a candle that we know the brightness of, and they measured its brightness and they put it on the Hubble's graphic.
Right.
Which proved that the universe was in expansion.
Okay, so let's just get into the physics because not everybody's an astrophysics professor like you two guys. First of all, how can we see how bright something was in the past? How can we measure it at different times? How do we do that?
With the wavelengths. Maybe.
So that's more about so what you're talking about is the Doppler effect, right? The
Yes.
redshift. So that's telling us more about the speed, right? The more it gets shifted towards the red, the faster it's moving away from us. The question I'm asking is more about how can we compare the way things are moving like 200 million years ago compared to 2 billion years ago compared to 7 billion years ago? Do we have a way of looking into the past to be able to compare this?
I don't know. I don't think so. Maybe we can like observe
We do have a way of looking in the past.
Oh.
We talked about this a couple of years ago in grade 10, right?
in grade 10.
Yes.
But grade 10 is like 15 years ago for us.
Oh, I'm sorry, but you look like you were my students only 2 years ago, right? You guys have been very well kept. So, Maud, do you have any recollection of how we look into the past? How can we look easily?
Maybe with the
into past?
light that reaches,
Right, so it has
Because,
to do with light.
because the time that the light is coming to
Right.
us is from the past, because the light was emitted like some time ago by the stars, but the time it takes to reach us.
Exactly. So the further something away is from us, the further in the past it is when the light reaches us, right? So if we look at something that is 2 million light years away, then we're seeing how it was 2 million years ago. But if it was 2 billion light years away, then we're seeing how it was 2 billion light years ago. So to compare, we have to look at a supernova, which is like at 20 million light years, and then another one at 400 million light years, and so on. So the two elements in there, we talked about how to compare it in time. And then do you want to just very briefly talk to us about redshift, what redshifting means?
Yes, so when something is moving away from us, its wavelength is going to be bigger,
Longer.
and we're going to like if we take the example of a car, if a car is moving away from us, the wavelength of the
The siren.
the siren is going to be longer, and then the frequency higher. And we're gonna hear.
And not only is it longer and higher, but there's actually a equation that tells us how fast it's going based on how much lower or higher the frequency would be. Right?
Yes.
And that's what we call the Doppler effect. And the Doppler effect is true for all waves. Sound is a wave. Light is also a wave. So for sound, it's the quality of the sound that changes, the musical note. For light, it's the color that changes. Okay, so we have observed that
stars were moving away from us because it appears to emit light that is shorter in wavelengths compared to a source of light that isn't moving. And because shorter wavelengths correspond to a shift towards the blue end of the spectrum, we call it blue shift. But when stars are moving away from us, the wavelengths shift to the red, and we call it red shift.
Exactly.
And it explained that the universe was expanding.
Right. So this is the observational grounds, which made people wonder what is going on. Gravity should make things fall in together, so it should not only make the universe expand faster, it should slow down the expansion of the universe, but we're observing the opposite. And so somebody comes up with the idea of
dark energy.
Okay, so let's get into that. Can you give us just a very short, brief idea what we mean by dark energy, what the properties might be, who it was that was involved with this?
So dark energy would be an energy, a force that works against the gravitation. And some theories were made about its constitution, its density.
What year are we thinking about the first ideas of what it might be? Like, was implied in this?
1990s.
Okay, so it's much more recent than
yes.
dark.
Yes, and the density of the dark energy would have to be constant because the density of like visible matter reduces with the expansion of the universe because it is diluted in the expansion. But the density of dark energy is constant.
Okay.
And in order to make the universe expand, the pressure of dark energy would have to be negative.
Right.
And that's the two major observations that were made by scientists.
So basically what you're saying is that we look at what we're observing and we're saying in order for these observations to make sense, this new force has to have these properties.
Yes.
Have we observed anything that has these properties?
Yes.
That's interesting.
These properties correspond to the ones of vacuum energy.
Right.
So as an astrophysicist, I totally understand what vacuum energy is. I think it's zero energy point. No, zero, like the lowest point of energy in
the lowest energy
in a field, but it's not like a zero energy.
Right. So you're saying that in the vacuum where there's we can see there's no matter, we would assume that the lowest possible energy would be zero energy. But what you're saying is that the lowest possible level of energy, even in the absence of matter, is not zero. It's higher than zero. And this is what we call vacuum energy.
And so the vacuum energy has properties that match the one of dark energies, but
we observed vacuum energy. We've measured it.
Yes.
Okay.
And when scientists calculated the density of vacuum energy, they find that it was 120 orders of magnitude bigger than the one of dark energy.
Okay.
So even if this model would have been perfect, we see that it's not the most accurate.
Okay. Okay. So it could be a potential candidate, but it doesn't match what we observed, the properties of this.
Yes.
So it can't necessarily, it has to be either something else or something else as well. So in addition to this. All right. So, oh yeah, Maud, you have a question.
Besides the vacuum energy, is there any other possibilities of what could be dark matter?
Yes, the other...
Dark energy, yeah.
Yes, the
Back to dark matter.
other theory is quintessence.
Right, quintessence.
Quintessence. Quintessence
Now we're getting into really, really complicated
advanced,
and advanced physics, yeah.
Would be
I think we have units here.
field, yes, of course, where like the spin of the particles, because we know that the particles in matter have a spin.
It's a half integer.
Yes.
Like 1/2 or like -1/2.
Yes, and in quintessence, the spin of these particles would be null, and that would explain like the expansion of the universe. But
so basically, if we really, really simplify things to the point that it's almost not scientific, it's like the presence of a field that has this energy with properties that would correspond to what we need in order to explain this expansion. But quintessence is only a theory which we haven't been able to test yet, right? Or have we done tests to observe it?
No, but we know that like quintessence differs from the cosmological constant explanation of the dark energy because it is dynamic when the cosmological constant
so it means it can
is
change
a
in
constant.
time.
Yes.
Right.
So it didn't match with the equation that we have of the universe nowadays.
Right.
So this idea was eliminated.
You mentioned the cosmological constant. We're getting into really advanced stuff.
Yes.
Do you want to just give us a short idea of what the cosmological constant is, where it comes from, and what it means?
Well, it comes from the theory of general relativity by Einstein.
Right.
He first put it in his equations because he was convinced that the universe was like static and eternal, and the cosmological and all the solutions to his equations were like dynamic models.
Right.
And so he put the cosmological constant to make his solutions static models. And with the discovery of the expansion of the universe, he took it back.
Right.
Because he thought that he didn't need it anymore.
Right.
But after, with the discovery of the acceleration of the expansion of the universe, scientists realized that we have to put it back in order to explain its acceleration.
That's interesting historically because the idea of the universe expanding is something that dates to recent times. It was Hubble's basically observation, right? So when Einstein came up, what was accepted at the time was that the universe has never changed. It has existed forever. It's going to exist forever, and it's a static universe. And so his equations were saying something else. So he's like, oh, there must be something missing from my equations, which is why he introduced this constant. And then 10 years later, so that was 1915, and then 1925 or 1926, I think Hubble makes his famous observations, and he comes back, and there's a famous quotation of Einstein says, I think this was the biggest blunder of my life, right? But he doesn't make too many blunders, Einstein, because this, if we look at it in a mathematical way, it's just a parameter which basically tells us if the universe is going to expand, shrink, stay static. So as soon as we observe that there is some sort of a dynamic behavior to the universe, then we just have to find out what this value would be for this parameter. And okay, wow, we're touching on all sorts of topics here. What do you think? Maybe we should come back to dark matter?
Yes, of course.
So
I have a question on dark matter. Is there still, you talked about the history of the discoveries of dark matter, but is there still researches now?
Yes,
about it?
of course. But maybe before talking about researchers, we can talk about what, like the theories we came up with.
Right. Okay.
So we have three main theories about the components of dark matter.
Right. So you're talking about theories that would explain where dark matter comes from, what it's made of.
Yeah, exactly. What
Okay.
it is.
So the origins of dark matter based on physics that we know already.
Exactly.
Okay. So what are the three major hypotheses?
Well, we know that we're looking, I already said it, but for very heavy particles because we have to find a really big mass in the universe that does not interact with light as we can't see it, and that does not really interact with magnetic fields or
Any form of the electromagnetic fields, right?
Exactly. So we have the WIMPs, which stand for weakly interactive massive particles. Those particles, except for gravitational forces, they do not interact with any other forces. They do not interact with neutrons or electrons, and they are very heavy. They are non-baryonic particles, but it's very difficult to see them. So to do so, we have extremely sensible detectors that are gonna try to detect the energy created during a collision of two atoms.
So to be clear, WIMPs are theoretical particles that have been proposed, but we haven't yet observed them.
No.
We have experiments going on to
Yes.
try and detect them,
Exactly.
but they haven't given any positive results yet.
Exactly.
But if we do detect them, they could be a good candidate to explain where dark matter comes from.
But we would still have to prove that they are what is dark
Right.
matter made of. It's
Right.
if we find them, it's good, but
We'd have to find them somewhere and in the right quantities to explain the missing matter.
Exactly.
Okay. So WIMPs, which have a very original name.
Yeah, we also have axions. Those are particles that go from very light to very heavy. So if we find them, we would like to find them in the very heavy form, because if they're too light, it wouldn't be good enough to explain the mass that is missing from our universe.
Again, these axions, they
Yeah.
are theoretical particles. Have they been observed or no?
Well, there is the ADMX that is looking for them.
The ADMX. What is the ADMX? Sounds very...
It's a bit complicated, but
What is the idea behind it?
like the ADMX is this very big machine that is gonna try to find axions.
Okay, so it's a big experiment that's going on.
Exactly.
Okay.
So there is a resonant microwave cavity with superconducting magnets,
Always.
and they are gonna try to detect the transformation of dark matter in photons. So of axions in photons, because axions are almost electronically neutral particles, and that can change into photons if there is a very, very, very strong magnetic field.
Right. And I remember you guys were talking about that if they do exist, they should be very stable, but they barely interact with anything.
Yeah.
Okay.
So, like, it's quite complicated to detect them, but the ADMX already told us a few things about dark matter. So it helped us to eliminate some models for the axions, and the scientists in working at the ADMX hope.
Do you know where this is taking place, the experiment?
You not.
Okay, I'll look it up while we're talking.
No
Go
idea.
ahead.
The scientists working at the ADMX hope to eliminate more models of the axions within the next 10 years. So I don't think they're very hopeful about really seeing axions and trying to do some experiments on them, but they're trying to really see if they could exist, and if they exist, we'll know that, but not in the next 10 years.
It's not unlike the WIMPs. This is a theory that's well established for a good number of decades, so we know the theoretical background. It's just a question of, are we able to find experimentally that they exist or not? Do you have any idea between these and the WIMPs, which one would be a better candidate for... I'm taking away Maud's question. He said, go ahead, ask the question.
Among those two theories, do you know which one is like the best candidates
Dark matter.
for dark matter?
Well, I think the WIMPs are the scientists' favorite, because I don't know, they're really exactly what they're looking for.
Okay.
But there are more experiments done on axions, because we have more material and machines to do it, you know?
Okay. In any case, most of these are, let's be honest, they're very advanced questions, and I think as astrophysicists, you guys are not particle physicists, right? So it's not your domain of expertise. So if you don't know a few things about it, that's not a big deal.
But there is still a last one.
Right, which is also a very good candidate.
A really good candidate. It's neutrinos.
Right.
A neutrino is a particle that interacts only with weak interaction and gravity, so this is perfect. It is electrically neutral, and its mass is very, very small. The rest mass of neutrino is much smaller than all of the other we know.
Even electrons or any other like subatomic.
Yeah, I have an example. We estimate that the mass of 3 neutrinos is less than 1/1,000,000th of the mass of 1 electron.
Okay, which is already at 10 to the minus 30 kilograms. So we're really, really hitting the limit of what we can actually detect in terms of mass.
Yeah.
But we know that they exist, or is that a theoretical particle as well?
I think we know that they exist because we know that neutrinos interact so rarely with normal matter that we estimate that 100 trillion fly through our bodies every second without us noticing, and which makes them very difficult to detect. But it was a study was recently published saying that they could be too light, and that they would,
despite the great numbers of them that are flying around.
Yeah. They would be too light, and it's not sure yet, but it's possible that they're too light and that they couldn't really make that dark matter because it would be
It
just
would not be enough
Yeah.
to justify all the dark
Exactly.
matter. So it's interesting that between the three hypotheses, the three particles that are proposed, the one that is the one we know it exists. Well, we know it exists because we have tested it, and also because if it didn't exist, most of standard model of particle physics wouldn't work. We really need that for most things to work. You're saying that recently we're reaching the conclusion that maybe it would not be enough of it in the universe to explain all the dark matter.
exactly.
So in the end, we really have no idea yet what dark matter is, which is good.
Neither dark energy.
Yeah.
That's even a bigger deal, right?
Yes.
But this is good for physicists, right? Because that means there's work to do still. If we find everything, then there's no more work and we have to go find other jobs,
Yeah.
probably in Wall Street. And
Well-
that's never a good idea. So let's hope that, yeah.
I have a final theory about dark matter, but I don't really believe in it. I think it's like kind of science fiction, but you told it. I'm not particle physicist, I can
Right.
tell you.
We can,
But some people believe that there is a parallel world
Mhm.
made of dark matter having very little in common with the matter we know,
okay,
called like the hidden valley. The hidden valley.
okay.
But many scientists consider this as just a way to avoid answering questions.
Oh.
Yeah,
So it's in a way, it's kind of pseudo-scientific because we can't actually test this out, right? So it is indeed kind of science fiction. Okay, all right. So let's come back to dark energy, because dark energy. So let's come back to the very, very beginning. So the universe is made up of what we can see,
Visible matter,
visible matter,
possibly dark matter,
dark matter,
and dark energy.
right. In what proportion do we think these should be?
We think that it's like 70% dark energy
Yeah.
and 30% dark matter and visible matter.
yeah. It's
But-
like 25% dark matter and
Mhm.
5%.
So basically, the universe that we see with these endless number of stars is basically like at best 5% of the actual
Yeah.
matter that makes up the universe.
That's why if these theories are true,
Mhm.
we would have discovered like
most of the universe.
most of the
Yeah.
universe. But if they're not, we only know 5% of our universe.
Yeah.
Okay. Or at least we can observe,
Yes, we can
because we've
observe
already
5%.
found some properties for these invisible stuff, even though we haven't yet been able to observe. All right. That's pretty mind-boggling to say that we can only see 5%, and what we can't see or interact, we can sort of detect, or we can infer the existence of because of our observations with the visible part. That's pretty impressive, right? So maybe we can move on to some questions, unless you have some more to add on dark energy.
Well, maybe we can say that like the only thing that they have in common
Yeah,
is their name,
right.
Yeah.
because clearly it's two different.
That's what physicists do, right? Like as soon as we don't know what something is, but
It's
we know
dark.
it exists, it's dark something, right?
It's funny.
dark holes and dark matter, dark energy. Yes.
It's funny because like I think people always think of dark matter and dark energy, things that go together,
Right, because
but they're really doing the opposite thing.
you're very right.
Like-
Very right. I think that's a very good point that you're making, because, like Domitille said, the dark energy would be responsible for expansion. It's like the word you used in your presentation was an anti-gravity force,
Yes.
kind of. And dark matter would behave just like normal matter in terms of it has a mass, it has a gravitational field, and that is why we can observe it indirectly, right? Because of these things. So that's a really good point. Even though they both have the same adjective, they actually have nothing to do with one another in terms of the effect that they have and what we can observe. Okay, that was a good point to make, I think. So, anything more to add before we maybe move on to some questions?
I think I just could speak about the LHC
Right?
because it's quite important in the search for dark matter.
Mhm.
So the LHC is the Large Hadron Collider. It's like a particle accelerator
Right.
in Switzerland,
Not
in
far from
France.
here, yeah.
And it's a very, very big thing. It's like 27 kilometers long. Fine. It's just a
Yeah.
very big thing. And in the same way, it aims at detecting particles
Mhm.
that could explain how dark matter is created and what would be its components.
Right.
So the LHC, in the LHC, they want to create particles that would escape through the detectors
Right.
because we cannot detect it. But as they escape, they would carry away energy and momentum. And physicists could calculate the momentum that is in
The missing momentum
Yeah,
and the
exactly.
missing energy.
And if there is some missing energy, we would know that we created dark matter, and that's it's
or the particles of dark matter, right?
Yeah.
Okay. Have we started these tests? Have we gotten
Yes.
results?
Yes. I don't think we've got
No, nothing.
really any results, but yeah, it started like maybe 15 years ago.
Okay.
But they had a
Still
few like,
waiting.
accidents and
Yes, we've talked about that recently as well. Very true. Very true. I think you had a question.
Yes, I would like to come back to a theory you explained, the neutrinos one.
Right.
Do you know what creates neutrinos and like where do they come from?
Yeah. So this was one of the three hypotheses, which is the one that we have actually whose existence we verified. So what are they? Where do they come from? Why do we need them?
so I think that neutrinos are created when some protons and electrons combine, and when they combine, some energy is taken, and you guessed it, this energy is made of the
In the form
neutrinos.
of neutrinos.
Yeah, exactly.
Okay.
So on Earth, most of the neutrinos we receive are from the sun with the fusion of hydrogen. But
Stars in general produce a lot of neutrinos, and there's one special event usually in the world of stars that produces a ton of neutrinos, which we use, which
the explosion of supernovas.
right, supernovas, which are the end point of the life of a star. They generally produce huge amounts of neutrinos which is some of what we have observed at some point as well. Okay.
Scientists also believe that some neutrinos from the Big Bang exist, but we cannot detect them.
We haven't yet.
Yeah.
Okay.
With our current technology. Some neutrinos are created from the contact between cosmic rays and the atmosphere,
Okay.
but that not a lot of them are created
Not
here,
in
but-
the portions that we
Yeah.
produce, for example, with stars or supernovae. Oh.
And neutrinos are also created in nuclear stations, but in very,
Right.
very
So basically, anytime we have particles being transformed from one thing to another, there's going to be emissions of neutrinos, right? It's a question of how much. When we do it ourselves, the scale is so small that it's almost impossible to maybe measure. But when it's in an astronomical scale, then that's where we can actually maybe measure stuff, or like astronomical scale of energies. Okay. I think there was a question also on vacuum energy that Maud had.
Yes, so you told us, Domitille, about the vacuum energy, but like a question I just asked to Jeanne, do you know where it come from? What are the origins?
Like, who came up with the idea of vacuum energy in the first place? I don't know if you came across it in your research.
Came up with it, but we know that vacuum energy is like the energy that we find in a place where there's no matter at all, and that the energy in this place is not null, as we could think. It is only like the lowest energy possible that we can find.
What is this? Where is it coming from? Is there something like carrying this energy, or is this the special field, the scalar field that you were talking about at one point, that could be what is harboring this energy, this vacuum energy?
I don't know.
Okay. No, we're getting into very, very, very advanced stuff, and I think already we have gone very, very far in what we're doing. Mo, did you have any other questions that you thought of while we were listening to your colleagues talk, or should we start? Yeah.
Maybe we can just add, Jane talked about the Big Bang, with where neutrinos were created, and maybe it's relevant to say that the discoveries of dark energy confirmed the theory of the Big Bang.
So they're compatible.
Yes, because the Big Bang theory is based still on Einstein general relativity and on a dynamic cosmological model. And when we found out that the universe was expanding, it meant that at some point the universe was dense and squeezed into a small place in order to...
The idea of the singularity at the beginning of the universe.
Yes, so it confirmed the Big Bang theory, which is our current cosmological model.
Okay, so that's a good sign. That means basically what you're saying is that even if we haven't found where it comes from, what it's made up of, it has to exist in a way, right? Because its existence is compatible with our current model of the universe, the origins of the universe, Big Bang and all that. So it's pretty good bet that it exists. We just haven't found out what it is yet.
Yeah.
Okay. Well, we have gone on for long. Any final thoughts? Yes, Jeanne.
Yes, I think we could finish a like with saying what those discoveries mean for us as like humans. For dark matter, I think that understanding dark matter is quite important to understand the size, the shape, and the future of our universe. The amount of dark matter in the universe will determine if the universe is open, which means it continues to expand, if it's closed or it expands to a point and then collapses, or if it is flat, which means that it will expand and then stop when it will reach equilibrium. And it can also help us to really try to see if our laws of physics are wrong or if they are right. Because if the motion of astronomical objects are wrong, our theory of gravity doesn't work on galactic scales.
This is a very interesting point that you bring up, because the reason we're so convinced that dark matter has to exist is because what we observe doesn't correspond with our laws of physics. But that goes both ways. Maybe the laws of physics are incorrect. And so, like we've seen in a lot of examples, like, we theorize the existence of something because we're doing the analysis wrong, because a law was missing some key element, and then when we changed our theory, then we were able to get rid of this so-called anomaly by correcting our model of the world. So maybe dark matter doesn't exist, and just really our laws of physics are incomplete, or laws of gravitation notably, right? Like basically, if dark matter doesn't exist, there's something wrong with general relativity, right?
Exactly.
Which is too bad for Einstein, but really good for a bunch of, young physicists who have new ideas and who want to make things better. Domitille, any final thoughts about your presentation, the topic, the research you guys did?
Well, just maybe that in either way, these discoveries have changed the world of science and will continue to do so. Right.
And I think it's a testament to our capacity to reach conclusions, even in the absence of a lot of visible observational stuff, and the way we're able to sort of reason our way to things. All right, so that was a really, really rich and enlightening presentation. Thank you very much to my host, Maud, who was a wonderful host, and to Jeanne and Domitille, who did a really, really good job on this. Thank you for listening, and hope to catch you next time with a new topic.
Bye.
Bye-bye. So, that is Physics Bites for this week. We hope that you enjoyed the episode. Tell us what you thought about the topic in the comments section. If you did enjoy the show, then subscribe to our podcast, tell all your friends about it, and leave us 5 stars. And most importantly, come back soon for a brand new episode.